In this post-lunch session, we are privileged to have Professor Mondal as our esteemed speaker. It's my honor to introduce him. Professor Nibir, who is structural geologist and a professor of geological sciences at Jadavpur University. He is known for his studies on the evolution of geological structures and is an elected fellow of Indian Academy of Sciences and Indian National Science Academy. CSIR, the Council of Scientific and Industrial Research, the apex academy of Government of India for the scientific research, awarded him Shanti Swarup Bhatnagar Prize for the Science and Technology, one of the highest Indian science awards for his contribution to the earth, atmosphere, ocean and planetary sciences in the year 2005. Professor Mondal did his graduate studies in the science at Jadavpur University in 1984 and obtained a master's degree from the same university in 1987. He continued at the University for the Doctoral Sciences as a CSIR Research Fellow, and after securing a PhD in 1991, he joined Allahabad University in 1992 as a lecturer, but he moved back to his Jadavpur University as a lecturer at the same year. He has been serving the university since then, holding the position of senior lecturer reader before becoming a professor of the Department of Geology, a position he holds today. In between, he did his postdoctoral studies at Hokkaido University as a JSP's visiting scientist at the ETH Zurich as a postdoctoral fellow. He also serves as an adjunct professor at the Department of Earth Sciences of the Indian Institute of Technology, Kanpur. Professor Mondal has significant contribution in the research on the evolution of geological studies. His studies have been documented in several peer-reviewed articles. You can access all of those through his profile link. So without further delay, we extend a warm welcome to Professor Nibir Mondal as he takes the stage to share his insights with us. So please.
Thank you very much. I'm really delighted to be at this university, at Aliah University, and this is my first visit to this university. So I'm really happy to be in this university and more happy to see so many young faces from schools. I'm a teacher at the university level, so I usually have rare opportunity to meet school students. A few days back, I was in ISN Kanpur, and there I had an opportunity to address some of the school students from there. So this is again another opportunity for me to talk among young minds. I chose this topic on earthquakes, which I'm going to elaborate, not in a formal way. It is not going to be a formal science talk. It is going to be a kind of, informal, something like in Bengal we call Adda. So that would be my motive, just to give you some, because in the school level, even we live in this earth, we know little about this earth. That's a quite surprising thing for me as a teacher, as an academician from our science community. And a few days back, the country has suffered a tremendous event, and I would like to start with some glimpse from that. Then we'll come formally. So let us. the incident that we have watched through videos naturally ignites our mind that what is the underlying cause of this devastating event. This is happening because of some fundamental physical processes inside the earth. And I believe that right from our school days, we should know the anatomy of the earth where we are having our entire life and the dictating forces of the earth that governs our lifestyles. So my motivation of today's talk is to provide you with some underlying science of the one of the devastating phenomenon that you have watched right now. So let us enter into these questions. What is the underlying science of the earthquakes? The earth has been experiencing this kind of what we call natural hazards. For geology's sake, we never call it natural hazard, but it is essentially natural processes. It must be happening because of the dynamicity of the earth. So let us go into that details. First, we'll try to learn what basically the definition of an earthquake, how this word has been derived, and then we shall venture into some physics about this phenomenon, which will take us to the most governing process, that is rupture dynamics, because we'll see that earthquakes happen because of catastrophic failure or catastrophic fracture inside the earth. So that thing we'll look at. And then we'll see that what is the connections of the earthquake, the way you have seen with the geological processes. And what kind of research that is going on in our country and also at the international level research frontier areas. So this is how we are going to make our discussions. And meanwhile, we'll be looking at some hands-on, deliberations to show you how the physics operates, what is the underlying physics that governs the earthquake generations. Okay. So, coming to the definition of an earthquake, the word quake, if you look at its etymology, it is derived from very old English word, quation. Quation means your shaking, trembling. So, earthquake is fundamentally some sort of tremors, that is some kind of vibrations, the way the graph shows, on the Earth's surface. Why that kind of tremors happen? Because of some impact of huge elastic energy. I'll come to that more in detail, right? And it happens catastrophically. It doesn't happen very long, wide time, geological time scale over million years. No, it happens within a few seconds time. I'll show you that what is the time scale in which earthquakes are triggered. So let us look at some simple laboratory experiments to demonstrate what I mean by the catastrophe, and then what is mean by the rupturing that I was talking about. So let us look at these simple laboratory experiments. And this is a solid material which you can compare with rock. And here we are giving a very incipient, cut to reproduce fracture, and it is subjected to some load. And the stress is increasing. In your 11th standard physics, you have learned that stress is proportional to strain. So this is how the strain is increasing, stress is also increasing, but it is reaching a point, critical point, where the stress drops dramatically. And this drop represents the failure of the system. And this is how the fracture propagates, what we are calling as rupture propagates. So when this kind of rupture develops, the way you are working down, you are giving energy to the system and was getting accumulated in the system instantaneously released as the fracture propagates. And that release happens in the form of waves. And the vibration keeps on moving. Let's look at this one. So, this rupture propagation, the way I was showing through the laboratory model, that happens in this manner. This is the incipient crack or fracture. And when it is under load, numerous micro cracks starts developing, forming clouds, as you see, and the density of cracks keeps on increasing, and at the threshold value, the crack propagates at a speed of sound. And as it propagates, the whole elastic energy that was accumulated before the crack initiation gets released at an instant. And the propagation of fractures can take place in technical language we call tensile fracturing, where the movement occurs across the fracture, and shear fracturing when there is a sliding motion. So these are the two processes which are responsible in earthquake generation. So shear fracturing in rocks, like you can imagine this is a fracture, and this is how the block moves one over another as fracture propagates. So this is how the rock block from one side goes in this manner, certainly. That we are going to see more in detail. So this is the conceptual presentation of how earthquake is generated in geological domain. So this is the rupture, the way I was talking about. And here, there is a sudden sliding motion. And as there is a sliding motion, the elastic strain energy gets released. And this is how they keep on propagating in the form of wave. These are waveforms. Just like you can imagine that in a pond, you are throwing a stone and waves are rippling, forming a concentrate waveform. So this is how the waveform keeps on moving and ultimately hits the ground surface, and the ground starts vibrating. The way all the buildings were vibrating, as you have seen in the video, right? Anyway, in a geological term, these kinds of ruptures or fractures called wall, where one block, as the red arrow shows, relatively moved over the other. That is called sleeve. So the amount of sleeve is going to decide what would be the magnitude of the earthquake. We'll come to that through mathematical equations. So in newspaper, you must have come across the term earthquake focus, epicenter, and so on and so forth. Earthquake focus is the point on the rupture surface where the strain energy gets released, like the red points represent the earthquake focus. And vertically up, you meet the point, what is known as epicenter. So epicenter, why is it important? Because epicenter is the most damaging, damage-prone area, because it is exactly lying above the focus. Okay, so I would like to show you some of the geological situations. Here you see that the whole block has gone down. This is a racing track in Japan. So this is one geological situation. You can see that this part has glided along this rupture. So this kind of rupture is called peak for earthquake generations. Similarly, this is kind of ruptures we see in rocks, geological sequence. This is a very important earthquake generating faults called San Andreas faults in the USA, in the western margin. And here you see that the road has been split, the house area has been split, the way you can see the lateral motion. And San Andreas fault is very famous in the USA because they continuously produce earthquakes. So this is another example in the Himalaya. This is the rupture, as you can see, and this is gliding over the other. These are old, geologically old ruptures. This is another example. Now let us look at the Earth's surface as a whole. The Earth's surface is not continuous; it is fragmented into pieces. As you see that, this is the overview of the Earth's surface, and they are fragmented by these, rough surfaces. And these are the locations for continuous generations of earthquakes. And here you see that this is beneath the ocean. Actually, beneath the ocean, we have lots of earthquakes, and that can trigger tsunamis. I'll show you some of the videos to demonstrate how tsunamis are generated because of the earthquakes happening beneath the oceans. So this is beneath the mid-ocean, right? In geology, we call it as mid-ocean rings. So if we look at the type of ruptures we get in geological situation in the Earth, mostly three kinds. Here, this is the rupture where this block glides over this block, and the compression is like this. That means if you compress like this, the whole thing has to overlap, the way we see in the Himalaya. And here, it is exactly reverse. This goes down, we call normal faulting. And here, the block neither moves up or down, but they move relatively side by side. So these are the three kinds of situations we encounter the faulting process. And you'll be surprised to know that in Myanmar, I'll show you the details later on, the kind of ruptures that has triggered violent earthquake has happened because of this kind of motion. That one side of the continent has slided like this. That has created the earthquakes. So anyway, so these three kinds of ruptures can form in different stress conditions. I'm not going into that. This is not necessary. So now, let us go more into the physics. So this is the rupture surface, as you see. This is taken from an earthquake event in the Himalaya in Nepal. And these contours represent the amount of sleep, right? Now, when there is a glide, we should not assume that this happens very uniformly. In fact, the sleep patterns is going to decide that what would be the nature of the earthquakes. Sometimes you might have come across the earthquake happened as a single event. Just it hits the thing, it happens to continue maybe few seconds or sometimes close to a minute or so. Sometimes it happens, there is one pulse, then you get another pulse. So multiple pulses hit a system, like the last one in Myanmar. Also, there are two major pulses. So, the sleep is quite heterogeneous. This is the rupture surface. So the block lying above it has glided in a heterogeneous manner. The red regions are the most sleep area. So the amount of sleep area is going to decide the magnitude of energy release. Because this is a function of the area of the sleep, active sleep area. That's why it is necessary to understand whenever there is a fall, geologists try to understand what is the area of active sleep if the active slip area is very large, there is a chance of mega earthquakes where the magnitude can go even 8, 9 or so. It's a huge. So we try to understand that what causes the rupture surface to have this kind of very non-uniform slip. So let us look at the more deeper physics into it. This is the rupture surface, which is basically a fracture surface. It has some friction, and one block, as I have told you, that glides over that. In your higher secondary physics, you have learned that there is a frictional law. When the block is to move, it has to overcome the frictional resistance. But here, the light is more complex. That there is a sliding motion, but that doesn't happen uniformly. This slides, then gets locked, then again slides. So this happens in a leaping manner. And here you see that if we model that kind of motion, this is a frictional block, and the friction will depend on the normal stress. And this is connected to a spring. And why this spring is connected here? To represent the elastic deformation. Now when we pull it, the force, when it exceeds, because as you increase the length of the spring, the amount of force is increasing. Because this is a linear law between spring elongation and the amount of force. And when this force exceeds the frictional resistance, it starts sliding. And once it starts sliding, the spring collapses and the stress gets dropped. Then again it gets stuck and the stress builds up. Then again it happens. So this is how alternately it goes to a peak point, then drops, and the drop points represent the release of elastic energy. And this drop represents earthquake, what is pointed as EQ. According to this model, earthquakes happen periodically, as you can see here. That if we can predict the wavelength of this stress increase, we can predict the earthquake happening. But we virtually cannot predict an earthquake very, very precisely. We can say that this is the area where earthquake is possible, but we cannot say the earthquake is going to happen on this date, on this time, and so on and so forth, because of some nonlinear behavior of the system. So I would like to demonstrate this part. So let us look at this camera. So please let you look at here, this part, I hope you can understand this part is representing spring, alright? And this part is representing a spring, elastic substance. So when I'm pulling it, what is getting accumulated? Elastic strain energy. When I'm releasing, elastic energy is released. So you can think reverse way, that I am stretching means I am giving elastic strain energy into the system, right? And then strain energy gets released into the system. So when at certain period of time, the strain energy is continuously accumulated into the system. This is how tectonic movement is happening, and elastic strain energy is getting stored, and this happens over billions of years. And this is how this amount of elastic strain energy is stored in the system. Now when this frictional block suddenly slides, the amount of energy got accumulated gets released instantaneously, and this energy travels in the system in the form of waves. And I'll show you what is the nature of elastic waves. That is known as elastic waves, mechanical waves. There are different kinds of waves like electromagnetic waves. So earthquake waves is essentially a kind of elastic waves. Okay, so let us see that how this sliding happens the way I was demonstrating. So simple experiments, you can do it at your home also. So why I am making this way? There is a coefficient of friction, and the friction is F is equal to mu into R. R depends on the weight. So this is how I am increasing weight, means friction is being enhanced, frictional force is being enhanced, which will act against the elastic force. So this is how there will be two forces that they will counter to each other, right? We are doing very simple experiments of Indian nature. The way I was demonstrating that this string will be continuously pulled, but this slider will not continuously. It will move like this, then stop, then this pull, then again this side, then stop. So this is how there is the alternate motion. The way I have shown, the curve was going like this, then drop, like this, drop. So when the curve was going up, that means the stress is increasing, because stress is proportional to elastic strength. So this is how when I am pulling, elastic stress is increasing. But as soon as it slides, then elastic stress drops immediately. And in your physics, you have learned that stress into strain, that's the energy. That amount of energy, as I said, will instantaneously release at the moment which slides. that's how we are going to demonstrate. Let us see whether it is happening like that. So I hope you can appreciate that that roller is being rolled to pull the thing, and it is being stretched. It stops. You see that this is, then again moves, stops, but this is being continuously pulled. You see this one. Okay, I am showing you a more refined version, right?
Subduction zone, megathrust. A fundamental rule of earthquake occurrence is that tectonic motions of plate interiors are steady, changing only subtly over millions of years. But at plate boundary faults, the plates are stuck for hundreds of years and then suddenly slip forward in an earthquake. Why does this happen? Well, this model, Quakecaster, seeks to explore and answer this question. This model contains the minimum number of physical processes needed to reproduce.
So this is exactly
to
what
represent
we are
the steady plate
demonstrating
motions,
here.
we have a fishing reel, which we can crank at a constant speed. The friction within a fault is represented by a granite slider with a rough bottom surface in contact with a rough rock surface. The Earth's elasticity is represented by a rubber band. At the start of this video, you saw a 2-slider earthquake. But what do you think would happen if we had a 1-slider earthquake, if we removed half the mass within a fault? Yet, there's the same amount of friction, the same Earth's elasticity, and the same steady plate tectonic motion. Let's find out.
So here you see
So
that.
as you can see, the single slider earthquakes are more frequent but smaller than the 2-slider earthquakes. However, this rarely happens in an actual fault. Usually, there are multiple earthquakes
And
that
I
occur
told
in
you
series
that
along with faults.
this
And these
one is
earthquakes
quite
converge with each other
heterogeneous
through the
because of
transfer of
the
stress.
very non-uniform
Quakecaster can
slip
demonstrate
pattern.
this
This
stress
happens
transfer
because of the
by attaching
multiple
sliders
slip
in series.
surfaces as you can see here. There are two, you can imagine that this is one slip.
Now that showed some really interesting Earth behavior. What we saw was tension building up on the first rubber band, which caused an earthquake with the first slider, which increased the tension on the second slider, which eventually slipped, and now reduced tension on the first slider, which increased the tension on the third slider, and the third slider eventually slipped forward. Now sometimes we see really irregular behavior. For example, sometimes we saw 2 sliders occurring at the same time, or even 3. So that represents 2 or 3 earthquakes occurring simultaneously along a fault.
So please look at this one, how the curve is going. Energy release. At the moment, it's like energy release. So when you have 2 sleeves like this, energy release doesn't happen simultaneously. There is a time gap, and that's why when we have an earthquake event, we have multiple pulses of earthquake stop. So that's why I told you before we came to this point that the sleep is quite heterogeneous, and that's why earthquake events are quite nonlinear in terms of time as well as space. So let us move. I was talking about the energy versus earthquake magnitude, right? Sometimes we call the earthquake magnitude is 5.5, 6, or 7. The last earthquake that happened in Myanmar was 7.7 or 7.8. But I would like to take you to this figure. You see that this is the magnitude. You know, it starts from 1 to 9. Look at the amount of energy. This is in joules. And what is the difference between the energy for magnitude 1 and 9? I hope there is a huge difference. Like if you have an earthquake of magnitude 5 and if you have a magnitude of 7, but the energy difference is huge because it happens in the logarithmic scale, as you can see from these equations. So if you have these equations and if you take the 8.2 magnitude on Richter scale, because there are many ways we can scale the earthquake magnitude. This is the one for Richter scale. Look at the energy. 10 to the power 16 joules. It is close to the energy released by an atom bomb. So the damage that can be created by an atom bomb can be created by an earthquake. So how serious we should be to know about the science of earthquake. This is not only for the sake of knowing science, but this is also for the sake of our existence in this earth. Right? And when you look at, let's say if you look at earthquake in the Himalayan region, you will see that spectrum of earthquakes of varying magnitudes. But there is a systematic mathematical relation. This is very interesting. And this A is the number of earthquakes for a particular magnitude, let's say A, then this will hold this relation. And this is known as Gutenberg-Richter law. And as you can see that the regression is quite consistent. Okay? And this B value is very important. For example, here, some of you might have heard about fractal pattern. So if you look at the earthquake distribution in a particular area, maybe in Assam or Aliah or somewhere called San Andreas, and if you plot the magnitude of earthquakes as a function of its frequency, they will have a linear regression on log plot. And this power law distribution is a very characteristic of fractal distribution, as you can see from here. And the slope is defined as the B value. So B value is very important in earthquake science. Anyway, you may not be aware of these things. Now I take you to the physics of earthquake waves. What are these earthquake waves? As I began by saying that earthquake is nothing but some sort of vibration on the Earth's surface, and that's how the Earth's surface is set. Now, there are broadly two kinds of waves: body waves. These are all elastic waves, as you are seeing that these waves carry elastic strain energy. As you can see here, that the wave is going like each here and the building is getting set. So one kind of wave travels through the medium. That's why it is called body wave. And the other kind of waves, which, so this is known as, primary wave, like the vibration looks like this. And secondary wave or shear wave, here the vibration is perpendicular to the direction of wave migration travel. And this is known as shear wave, it goes like this. So these are the two broad types of waves. You can compare this kind of waves with light waves. As you know that light waves is basically a kind of transverse waves. And sound wave is like this one. You can compare this as sound wave, and this one you can compare with a light wave. So let us look at some movie. So this is how a longitudinal wave or P wave propagates through the medium. I hope you can understand. The compression is traveling, as you can see here, it travels. So energy is getting migrated in this manner and released here. But here, the H wave migrates in this manner. I hope you can understand. So these are the two broad kinds of earthquake waves propagated. When there is an earthquake an event, as I have shown you, the elastic spin energy travel in the form of waves, and these are the waves. There are two kinds of waves. One is sound-like kind of wave, what we call as longitudinal waves or P waves, and the other kind of wave is like light waves, that is transverse wave. It moves in this manner. We call it a shear wave, because shear deformation happens. Now the other kind of wave, which is more fatal during earthquake event, the tall building that we are saying were shaking, was not because of P wave or S wave that I showed. It is because of your surface wave. And surface wave, the wave that travel near the surface, the way you are seeing, and there are two kinds of surface wave. This vertical motion takes place and the wave travels in this way where the particle motion is happening counter to the wave motion. This kind of wave is called Rayleigh wave. I hope you have heard the name of Rayleigh scattering in physics. And this is love wave. Instead of there is a vertical motion, it happens in this way. So if you have a tall building and it is hit by surface wave, Rayleigh wave will cause the building to oscillate in this manner. The way you have seen there in the first video, it will be like this. And if it is hit by love wave, then the building will twist like this. So there is a complex motion that happens during the earthquake event if you have a tall building. Okay, so I would like to show you the motion. This is how you see Rayleigh wave. Look at the motion of the black. And this is how the lateral motion, as I said. Now, I'm leaving these all mathematical things. However, I believe that from your physics knowledge in 11th, 12th standard, you can at least, appreciate this kind of, mathematical thing. That compressional strain happens in this way, longitudinal strain, and this is how shear strain, and this is how the relation between compressional stress and shear stress, as you can see from the diagram. And this is how P wave travels by pressure in this way. Please bear with this kind of pattern. And this is simple wave function. I hope all of you are familiar with this wave function. And this function must satisfy this second order differential equation, what is known as wave equations. Okay? And let us draw this one. Let us go. And what I wanted to tell you that the velocity of the primary wave depends on bulk modulus and shear modulus. And shear wave velocity depends on the shear modulus and density. The wave, for example, if we take the transverse wave, the velocity of that wave will follow this equation. I have a question for you. Can a shear wave travel in water? Can a shear wave travel in water? Yes or no? You look at these equations. The velocity of a shear wave depends on shear modulus divided by density. Does water have any shear modulus? Then what should be the velocity? 0. So shear waves cannot propagate through water. So whenever there is oscillation because of earthquakes, in the swimming pool that we are seeing, or in ocean, this is not because of shear wave, but this is because of primary wave. Because shear waves, transverse waves, cannot propagate through any liquid medium or any fluid medium. But we can hear you, or you are hearing me, not because of shear wave, but because of the primary wave. That is, sound wave is basically a primary wave. It oscillates in this manner. These are very fundamental physics. So this is how, if you have an earthquake, let's say in the Himalaya, there is an earthquake, the body waves will travel in this manner, and we are here, let's say Kolkata, and we'll get the shake. And it takes some time. And the velocity, if you look at, it is in the order of 8 kilometers per second in the upper level. So you can calculate, if there is an earthquake now, then when you can get the shake, you can easily calculate the time. And this is how geophysicists predict that if there is an earthquake, but the time is not very big, it is in the order of few seconds. Because if you look at the speed, 8 kilometers per second. Okay, so now I'll give you, because as a school student or as a science student, you should know that how earthquake is recorded. And the instrument that is used to record earthquake is known as seismograph. And what does it contain? It contains two things: seismometer. What is a seismometer? That detects a ground vibration and amplifies it. I'll show you. And this thing is converted into graphical thing, which you can see in a visible record, what is known as seismograph. So these are different kinds of instruments, right? And here you see that this is fixed here, and if there is a vibration, this mass will remain stationary, but this will keep on vibrating, and you can see the thing. And there is a more sophisticated seismometer nowadays being used, electromagnetic, because this will vibrate, so there will be change in electromagnetic flux, and that will create electric pole, and that can be converted into, shake. A similar thing you are seeing here. So I would like to show you. So this is the real thing. Let me show you. Check. So please look at this one. So that this is vibrating, and this needle is leaving the imprints. And you see that this is somewhat white now. So the whole drum is rotating in this manner, like this, as a function of time. You see that there is an upward. So this is how the whole thing. So this is how we can precisely determine the time at which the place has been hit by a downward event. So this is the time of the most damaging instant, you know. This is the point where the surface wave has hit the ground. So because of time, I am stopping this one, right? So this is a typical loop of a seismogram. I would like to show you some of the basic elements in this graphical plot. Here is the start of the earthquake event. And the first signal that comes from the primary wave, and that's why it is called primary wave. And then you have a secondary wave. And here you look at big peak. And what are these peaks? These peaks are represented by surface waves. And what are those surface waves? Rayleigh waves and lava waves. So most of the damages that happen during an earthquake event, the way you have seen that building has collapsed or the building is oscillating in this manner because of these waves. So that's how, if our technology is developed to locate at what instant the place is going to experience the attack of surface wave, at least we can make some preparations. But the unfortunate part is this, the difference between this and this is in the order of few seconds. That's not a very big timing error, that's the problem. Okay? Now I'll talk about some geology, then try to finish our discussions. Now if we look at the overall earthquake distribution in the globe, earthquakes do not happen everywhere. Like earthquakes do not frequently happen in Kolkata. But they happen particular areas, like you see that earthquake is happening here, here, here. They form some belts, right? Where we are here. India is here. And most of the earthquakes that we see are localized in this area. And I hope you can understand this is Andaman. Andaman is again another earthquake-prone area. And this is how geologists are trying to understand that what is the connection between earthquake and the geological processes. For example, here, this is the Pacific Ocean, this is Atlantic, and this is Indian Ocean, right? And if we look at here, this is a huge earthquake activities going on here. Similarly, huge earthquake activities are going on. Why? Why not here? Why not here or here, but localizing here? That we need to understand. Now, if we look at this portion, this is South America, continental mass. The geologists have shown that this part is heading towards this continent, and at one point, this is sinking into the, and this process is known as subduction. Let us bother about the terminology. But because of this, motion, there is a related motion between the two. So that's how there is a frictional sliding, and that gives rise to earthquakes and to great depth. This depth can be in the order of 300 kilometers, or even it could be 600 to 700 kilometers. So geoscientists have been quite successful in predicting that the earthquakes can happen where the depth can vary to even to 600 to 700 kilometers. Let us come back to our country. And here I have shown you that the this is the earthquake prone area. And if you look at the earthquake focus distribution, it is, and here you see that these are all big earthquakes, 2005, similar 800, 1800, and probably Kolkata got a major damage because of this earthquake, even maybe some 1800, this one. You may find that mention of earthquake even in Rabindranath Tagore's writing. Okay. Anyway, so if we come to the Himalayan section, it is like this. India is here. This is your Tibetan part. This is Nepal, and this part is gliding over there, the way we were seeing. And because of this gliding motion, there is a strain release, creating earthquakes, and which is clustering. We are clustering mostly in this region. So in the Himalaya, the earthquake is quite predictable, at least on a broader sense. We cannot exactly predict that the earthquake will happen just here, just at this moment. That we cannot do. But we can at least predict that this is the area where earthquake is likely to take place. So similarly, we have in the Tripura fault belt, Tripura is here on this side, here, in this side, and here the plate is going in this manner, and you see that these are all earthquake foci, and they are nicely correlatable in the movement directions. Okay. And this happens in August 2016. In fact, some of the geophysicists have predicted. I would not like to see their prediction becoming correct. And this paper appeared in Nature maybe a few years back. They are predicting that this is the gliding surface. It is now locked here. And this will start sliding within a few years' time, and this will reach Dhaka. And if that happens, so it will create life loss in the order of millions. So this paper appeared, and I had some review on this paper, and there are many criticisms, and nobody can claim that this should be correct. So let us not welcome this paper in that sense, because if it happens that this is creating a huge loss of life, unimaginable. Even Kolkata will get affected because the rupture will propagate up to the city of Dhaka. So this is the overall Himalayan earthquake. So many earthquakes. That's why I told you in the beginning, earthquake for a geologist is not a hazard. It's a common natural process. Because the earth has to release its energy. So how can this energy be released? One of the mechanisms to release energy is to create earthquakes. And that's how you get so many earthquakes. And I would like to mention the major earthquake that happened in 2015 in Nepal, when Kathmandu was sacked absolutely, and many buildings got collapsed. And this is the sleep area, as I have told you. I showed you in this area. And the paper appeared in Nature Geoscience in 2016. In fact, the day this earthquake happened, I was taking a class in the top floor. And the topic of my class was how earthquakes are produced. When I was delivering that kind of thing in the classroom, I started saying that the fans started wiggling like this. And the whole building is an old building, that's why our building is slightly oscillating in this manner. So it was a very miserable coincidence that when I was taking a class on earthquakes, and earthquakes have started forming, shaking the building. So that's a very big. And this is how I have shown you that this is the particular locations where earthquakes are produced in the Himalayan region. And this is the overall picture of the Nepal earthquake. And here is the Everest base camp on the corner, and this is the slip plane, sliding plane, and this is below Kathmandu, and Kathmandu was the city very close to the epicenter. Right? Now I'll take you to the video that I showed, the Myanmar earthquake that happened this year, a few days back. And this is the overall scenario. This is the place of this country. And this is the rupture I was talking about. And this rupture created the earthquake. And if you relate here, this is the overall view. The Indian plate is subducting in this manner, and there is a rupture. This is a sidewise movement, what is known as sagging fault. And the sagging fault, if you look at the motion, is like this. And what you can relate with this one. So this is the culprit to create that devastating earthquake that we have seen in the beginning. Okay, and I hope you can relate. This is a bridge before, and this is after. The whole thing has like this. Similarly, this is another one. This construction has get before and after. So now coming to the end point of the research in India. In India, research on earthquakes isn't it perceptible? The government of India is spending lots of money to detect mostly the earthquake-prone areas and different kinds of measures, warning system, and all these things are being developed. And many physicists are engaged in finding precursors for detecting earthquakes, etc. At international level, I would like to show you one thing, that tsunami research is one of the major
Subduction zone megathrust earthquakes.
So let us look at how tsunamis are produced, and
a variety of structures that are based on several models.
So
The
this
basic
is how you
shows
see
rock
that the
bubbles
elastic strain is
being
getting accumulated.
compressed
As the
and
plate is
fed as it
moving,
stores
the whole
elastic
thing is
energy.
getting compressed.
Once friction is
And the
overcome,
elastic
the
strain is
overriding plate slides abruptly
Yes,
up
then
fault,
certainly
causing
it
the
moves.
leading edge to heave
And you see
seawater
the waves are being
upward,
created.
generating a tsunami. This shallow angle reverse fall is called a thrust fall because the overlying plate thrusts up over the subducting plate. Let's explore different tsunami-producing mechanisms by examining 3 famous earthquakes. In 2011, the magnitude 9 Japan earthquake ruptured a fault area 500 kilometers long by 200 kilometers wide over an interval of nearly 3 minutes. Surveys of seafloor bathymetry before and after the earthquake document up to 50 meters of fault displacement at the Japan Trench. What would that look like in cross-section? During the rupture process, the overriding plate slid up the west-dipping fault plane. That uplifted the seafloor by 10 meters, producing the local tsunami that rushed on shore within 20 minutes of the earthquake. Next, let's examine how deformation, as well as fault displacement of the overriding plate can produce a tsunami. The 2010 magnitude 8.8 Chile earthquake tore a rupture zone 600 kilometers long by 130 kilometers wide. Although the rupture began at approximately the same distance from the trench, there was little to no displacement at the trench as there was during the Japan earthquake. So, what generated the local tsunami that resulted in 123 deaths and produced major damage in coastal towns? Fault displacement ranged from 5 meters at the hypocenter beneath the coast to 10 meters midway to the trench, then decreased to little or no displacement at the trench. Westward displacement of the continental shelf above the plate boundary caused broad uplift of the seafloor. In addition, the change in amount of displacement along the plate boundary caused internal deformation of the overriding plate. These effects combined to uplift the ocean floor by 2 to 3 meters.
This sudden uplift generated the deadly local tsunami along the coast of South America and Juan Fernandez Islands. Our third example introduces splay faulting during the rupture. The 1964 magnitude 9.2 Great Alaska earthquake ruptured a major segment of the eastern Aleutian subduction zone, 800 kilometers long, lasting over 4 minutes. The continental shelf and slope of the overriding North American plate was uplifted over 9 meters, while inboard areas subsided as much as 2 meters. This sudden displacement of the ocean floor generated the tsunami that claimed lives from Alaska to Northern California. Less than 2 meters of regional uplift occurred at the trench. So what caused the 9-meter uplift of the continental shelf and generated the tsunami? In this example, we will show that there were 3 contributing factors to the devastation that ensued. With few seismometers in the region in 1964, the progression of the rupture relative to the splay faults is unknown. For simplicity, we'll show plate boundary displacement branching into splay faults. During this earthquake, displacement started on the plate boundary megathrust fault, producing 2 to 4 meters of regional seafloor uplift at subsidence. However, most of the fault offset ramped up to the seafloor on splay faults like the Patton Bay Fault that was displaced 9 meters. Because displacement on steeply dipping splay faults causes larger uplift of the ocean floor, a bigger tsunami is produced, and it starts closer to shore, providing less time to evacuate. In steep-sided fjords and inlets, ground shaking caused landslides, some entirely below sea level, resulting in surges of seawater up to 50 meters high that struck coastal towns, including Seward and Valdez. The tsunami-producing mechanisms illustrated here are still just a glimpse into the variety of subduction zone earthquake faulting and folding processes.
Okay, so let's get back. In the international platform, unlike India, they are doing huge experimental and theoretical studies on earthquake generation, on earthquake mechanics. Unfortunately, that kind of rigorous research is not happening in India. Even we are having many surveys and many stations almost along the entire span of the Himalaya. But the way the West countries, mainly researchers from the USA and some countries from Europe, they are doing, like this one. This is how this is a numerical modeling of how a rupture, as your rupture is nucleating and propagating, and ultimately meeting the surface, creating the shaking of the ground. And as I was telling that the time is very less. Now you see that at this time instant, 3 seconds, the rupture has nucleated, and it is heating the ground surface almost after 6 seconds. So what you can do, if I tell you that yes, the rupture has localized now, so you have only few seconds, maybe in your 5 to 6 seconds to prepare yourself. But nowadays, I have heard that the USA particularly, they are developing a warning system through mobile and etc. Whenever there is any nucleation of ruptures, releasing some energy that would give a signal to all people, and so that they can prepare themselves to counter to the major event. So this is how you see that now when the surface waves have hit the ground, the tree has fallen down. And this is how they are also, as I said, they are also doing experiments to understand how the failure and rupturing can happen. Just a glimpse for that. So this is how different kinds of experiments, laboratory experiments, are being conducted, like this one. And the major focus is this, that how can a fracture propagate and release the energy. That's the idea. Okay, so this is how they do. I'll spend a few words on this. that when there is an earthquake or generation, let's say in Assam there is an earthquake, and it starts propagating. Do they propagate with the same amplitude? The answer is no. There is a phenomenon called attenuation, that the amplitude of the waves keeps on decaying exponentially, the way you see here. So this attenuation property depends on the materials. For example, we have in Kolkata loose material. So these loose material have greater attenuating properties. So that's how researchers who are engaged in this kind of research of seismic hazard donations, they are quite concerned about this attenuation. So as I said that in India we need to have a very strong foundations for theoretical and experimental approaches, not only in the academic curricula, also research like Aliah. Thank you very much.
Now this session is open for discussion. If you have any question, you can ask to sir. তোমাদের যদি কারো কোনো কোয়েশ্চেন থাকে তোমরা স্যারের সাথে ডিসকাস করতে পারো।
হ্যাঁ, আমি বাংলায়ও কোশ্চেন করা যেতে পারে। আমি ভেবেছিলাম বাংলায় বলবো, তারপর দেখলাম বাংলা বলাটা মানে এক স্টেজ, মানে যেহেতু সায়েন্সের টার্ম আছে সেহেতু বাংলায় একেবারে বলাটা একটু ভেঙে ভেঙে যাবে। কিন্তু আমি প্রথমে ভেবেছিলাম বাংলা বললেই ভালো হয়, কিন্তু আমি জানি না যে এখানে কতজন বাঙালি আছে বা বাঙালি আছে, সেই জন্য আমি ইংরেজিতে বলার সিদ্ধান্ত নিলাম। তো তোমাদের যদি মনে হয় যে বাংলায় প্রশ্ন করলে তোমরা ভালো লাগবে, তো আলোচনা করা যায় বাংলা। হ্যাঁ, earthquake measure করা হয়, এটা is a very nice question. How do we measure the earthquake magnitude? I hope তোমরা জানো যে ওয়েভ মেকানিক্সে একটা ওয়েভের এনার্জি নির্ভর করে তার অ্যামপ্লিটিউডের উপর। তাহলে আমি যদি অ্যামপ্লিটিউডটা যদি বার করতে পারি ওই যে রেকর্ডার শাস্ত্রগ্রাম থেকে, তাহলে সেই অ্যামপ্লিটিউডকে আমি এনার্জিতে কনভার্ট করতে পারি। এই এনার্জিটা যদি পেয়ে যাই তাহলে ওই ইকুয়েশনসটা দিয়ে আমি এমটা বার করে দিতে পারি। সেহেতু ম্যাগনিটিউড বার করার প্রথম যেটা ধাপ হলো to measure the amplitude of the waves যেটা পাচ্ছে আমরা disturbance in this seismogram, সেই অ্যামপ্লিটিউড থেকে আমরা যেমন সারফেস ওয়েভের এনার্জিটা বেশি, সেই জন্য অনেক উপরে থাকে।
আরেকটা কোশ্চেন, এখানে আপনি বললেন যে রার ফ্র্যাকচারগুলো এনার্জি রিলিজ করে, এটা কেন করে এনার্জি? এইভাবে তো আরেকটু ডিসকাস করলে ভালো।
আচ্ছা, আমি তাহলে আবার এখানে যাই। এইটা যখন টেকটনিক মুভমেন্টটা হচ্ছে তখন তো হয় কম্প্রেশন বা টেনশন, যেটাই আমি টেনশন করছি আমরা একটু সুবিধা করতে, তাহলে এই এনার্জিটা আমি তো ওয়ার্ক ডান করছি। ফোর্স ইনটু ডিসপ্লেসমেন্ট ইজ ওয়ার্ক ডান, এটা ফিজিক্সের বেসিক ল। তাহলে এইখানে আমার ডিসপ্লেসমেন্ট হচ্ছে, তাহলে ফোর্স, আমি একটা ফোর্স অ্যাপ্লাই করছি আর ডিসপ্লেসমেন্ট হচ্ছে, তাহলে এনার্জি যাচ্ছে। তাহলে এনার্জিটা কোথায় আছে? এনার্জিটা এর মধ্যে আছে। তাহলে আমি যদি এটা 30 দিন ধরে আমি এরকম করে যাই, তাহলে 30 দিন ধরে এতটা এনার্জি জমা হয়ে আছে কিন্তু এর মধ্যে, কারণ এটা ইলাস্টিক সাবস্ট্যান্স এনার্জিটাকে স্টোর করে রাখে, নষ্ট করে না। কিন্তু যদি ফ্লুইড হয় তাহলে এনার্জিটা নষ্ট হয়ে যায়। এটা ইলাস্টিক সলিড বলেই এই এনার্জিটা এর মধ্যে, ব্যাংকে যেমন টাকা জমা থাকে তেমনি এখানেও এই এনার্জিটা এর মধ্যে রয়েছে। ব্যাংকে যদি এখনো সানসারেন হয়ে যায়, কিন্তু এখানেও ট্রান্সফার। তো যাই হোক, তো এইটা যখন এটা ক্রিটিক্যাল, এটা ফ্রিকশনাল রেজিস্ট্যান্সটা যখন অতিক্রম করলো তখন কি হবে? এটা সরে গেল, তাহলে এই লেন্থটা কমে গেল। এবার এই লেন্থটা কমা মানে হলো যে অ্যামাউন্ট অফ এনার্জিটা ছিল বাজেটে তার কিছুটা অংশ বেরিয়ে গেল চট করে। তাহলে এই যে মুহূর্তে এটা সরলো, এই মুহূর্তে এতটা পরিমাণ এনার্জি রিলিজ হলো, কারণ এইটা হলো ডিসপ্লেসমেন্ট। আর ফোর্স যেটা ছিল, ফোর্সের এগেইনস্টে ডিসপ্লেসমেন্ট হয়েছিল, তাহলে force into displacement that energy gets released.
Thank you.
And এই রিলিজটা হচ্ছে একটা ওয়েভ ফর্ম। যে কোনো সাডেন জিনিস আপনি যদি এখানে এই যে মানলাম এখানে একটা সাউন্ড হলো, কেন হলো? এই যে এরা এনার্জি দেন করে ডিস্টারবেন্সটা ইয়ারটাকে রিপ্লিক করলো, তার জন্য একটা সাউন্ড তৈরি হয়। একইভাবে ওখানে
আপনি একটা কথা বললেন যে আর্থকোয়েক ওটা একটা মানে মানে কোনো হ্যাজার্ড নয়, ওটা একটা ন্যাচারাল ফিনোমিনা, কিন্তু আর্থকোয়েকের পরে তো মানুষের ক্ষতি হয়, তাহলে আপনি কিভাবে বললেন যে ওটা কোনো হ্যাজার্ড কি নয়?
প্রথম কথা হলো যে আর্থকোয়েক যদি না হতো তাহলে কি হতো সেটা ভাবা যায়। আর্থকোয়েক হওয়ার যেটা আমি দেখালাম যে একটা প্লেট আর একটা প্লেটের সঙ্গে রিলেটিভ মোশনের জন্য। তাহলে যদি আমি আর্থকোয়েক না চাই তাহলে আমি প্লেট মোশনগুলো বন্ধ করে দিব। তাহলে পৃথিবী হয়েছিল অ্যাবাউট 4.6 বিলিয়ন আগে, তারপরে এই প্লেট মোশনগুলো শুরু হয়েছিল অ্যাবাউট 3.5 বিলিয়নের সময় থেকে। তাহলে এই প্লেট মোশনগুলো যদি না হতো তাহলে ভলকানিজম হতো না, আর ভলকানিজমের জন্যই আমার কন্টিনেন্টগুলো হয়েছে। তাহলে কন্টিনেন্ট যদি না হতো তাহলে আজকে এই কলকাতাও তৈরি হতো না আর ইন্ডিয়াও তৈরি হতো না। তাহলে ডাইনামিসিটি অফ দি আর্থ এটা কিন্তু খুব নেসেসারি থিং ফর দি প্রোডাকশন অফ কন্টিনেন্টস এন্ড আদার প্রসেসেস টু হ্যাপেন। ইভেন যে লাইফের যে ডাইভার্সিটি এসছে সেটাও কিন্তু এই মোশনের জন্য এসছে। এবার আর্থকোয়েক ন্যাচারাল হ্যাজার্ড আমি বলতে রাজি না। এই কারণে আমি নিজেকে প্রিপেয়ার করি, আমি বৃষ্টি পড়ে আমি ভিজে যাই বলে আমি বলছি বৃষ্টিতে হ্যাজার্ড, সেটা কোনো কথা না। কিন্তু আমি যদি একটা ছাতা নিয়ে বৃষ্টিতে যাই, যে আমি যদি সেভ করি, তাহলে এই বৃষ্টির জলটা কিন্তু বেনিফিশিয়াল ফর দ্য ম্যানকাইন্ড। তাহলে